Hi everyone, we're back for another episode of Data Stream Live, and today I'm joined by Dan from Causa Tech. Dan, it's great to have you on. Your third guest now, getting a bit of momentum. Introduce yourself. Who are you? What do you do?
Yeah, well, thanks for having me on. Yeah, so I'm Dan. I'm the CEO of Causa, and so we're a York-based company, and we have a platform for doing causal AI. And I think we're going to talk a bit more later about what causal AI is. But essentially, we make it really easy for companies to implement causal AI with our help on our platform, and then it plugs into their software. It's all cloud-based, and it basically powers them with this technology.
Yeah, great. And you're York-based, right? So you're Yorkshire-based over at the Guildhall, I believe. How long have you been going?
We've been going maybe about 13 months now. So,
Okay.
yeah, a startup.
Going into your second year. And what were you doing before? You've
Yeah.
always done this.
So before so I spent kind of 21 years in academia. So originally I did a computer science and AI degree, and I became quite interested in actually the natural world. And so I moved on to actually doing a PhD that was half computer science, half life sciences, which is where this more scientific kind of AI and machine learning kind of first kind of interested me. After that, actually, I got a job at the University of York, where I was a professor for now 18 years, but again, like split half between life sciences and computer science. But then about maybe 2.5 years ago, I decided to try and move into the real world and make a real difference. So I moved to work for a company called Improbable, which is a unicorn startup in London. I did some. I was a researcher doing machine learning and modeling stuff there. But also at the same time, Jordan, who's my co-founder, I met him about 7 years ago. I actually taught him as a master's student. He was a mathematics master's student, and he took an elective in machine learning. So I actually taught him machine learning before he went on to surpass me. Then also as one of his PhD supervisors. But then he went on to work for an AI startup too. And that's basically where we noticed this problem everywhere, which I won't go into now, but we'll talk about later, which is what made us come together to kind of form Causa and make causal AI available.
Oh, fantastic. And touching on that then, the life sciences, have you seen any parallels, or is there anything you've learned from life sciences? Has that been your background that you've applied to machine learning, computer science, anything else? Because I'm fascinated that they say, in other industries and in other sectors, and there's a lot of things you can learn from each other that can be applied. Is there anything that you've seen that you've applied or could apply?
Yeah, I mean, totally. I mean, I've always been an interdisciplinary researcher. I've always thought that people should be looking to work across fields. A slight digression, but I think this is, when people are talking about large language models and Gen AI and whether you're going to get to this general intelligence, I find it interesting that it's mainly people just with computer science backgrounds that are talking about it, when it's more in the realms of philosophy and science and things. But that's a slight digression. But yeah, I've always worked across fields, and the thing about working in science is all of the questions are why questions, right? They don't want to just predict something. They want to know, how has this thing come about? What is the cause of it? And so that's when really you're not just interested in, is one thing correlated with another? You want to know, what are the causes of it? And that's where my interest actually in kind of causal statistics and causal machine learning came in. It's slightly different from in industry, you often don't really ask these questions of like why it's come about. You just want to be able to change something. But to change something, you need to be able to change the things that are the whys. Basically, you need to be able to change things to shape it. And so definitely that's for me, that's what influenced me heavily. In science, you basically do a lot of experiments. So you'll do these randomized controlled trials. In industry, they often call these A/B tests. But the whole purpose of these tests is to get at cause and effect. You're trying to balance anything that's not of interest between two groups, so that you can isolate the thing that you're trying to find out about, the cause, right? But often you don't have that, especially in the area I worked in. I mean, it's a bit weird actually. So I spent some time, well, 10 years working on killer whale data. This is long-term data on these killer whales, and it's you can't do experiments, right? We can't be fishing them out of the water or anything, but you still want to ask these causal questions without being able to do experiments. And again, this is akin to what we often want to do in industry. And you have all this observational data, which is not causal. And this is where you need these causal methods to be able to do to get to cause and effect without doing experiments, essentially. And so that's where I realize that is what we can be bringing over really into industry, because it's what's really needed.
Okay, so you mentioned it a few times. So I think let's dive into it straight away. I had loads more questions about life sciences and things, but we'll save that for another day. So let's start with before causal, right? Then pre-causal. How does AI and data science exist currently? And when we say AI, we're talking machine learning, right? We're not talking so much Gen AI and robotics or automation or anything like that. We're specifically talking for now machine learning. So do you want to let's start from the beginning? What is machine learning and how does it differ from anything else? I think a lot of people don't understand that difference between what we've had like pre-machine learning and the differences between that. Do you want to expand on that?
I think really you can sort of lump Gen AI in with all of this. It's a tricky thing because, like you say, most people these days, it's a very new thing that they equate AI with Gen AI, like large language models like ChatGPT. But AI is more than that, much more general than that, and it's actually just a specific kind of use case of it. Like machine learning is the thing that I would say the machine learning is the thing that leads to the AI, right? So in that case, they use something called a transformer, which is a bit like a neural network, but slightly different. But they're just doing the same thing as you do in all these other models. They're training it to predict the next word based on the last words, right? And so it's just a prediction or forecasting model. It forecasts the next word. So to me, it's a similar thing. It just has different application, really. And I guess there's been lots of development in machine learning and AI, but really to me, all AI is essentially just like a statistical model that can identify patterns and extrapolate, right? And again, the same with large language models. A lot of the uses of machine learning and even statistics is to essentially predict or forecast an outcome from a bunch of inputs, basically. So the typical approach is, you want to predict next week's sales or something, or you might have data on last week's sales. You might have data on, whether you're given any discounts, what your stock, what the weather is, and things like that. You shove all these into the model, and it looks for correlations between these inputs and the output, the thing that you want to forecast, which is next week's sales. And so I think that really, for me, there's not a lot of difference between statistical models, which have a lot of experience with machine learning models, which might be something like these decision trees where it decides which way to go based on the data to get to the outcome. Neural networks, which are sort of like digital representations of a brain, but really, really abstracted from it. To me, that's all a very similar thing, and it all boils down to kind of two key components. Whether it's statistical, machine learning, AI, you have to choose the representation for mapping. So it's like a function for mapping the inputs to the output. So that might be the neural network, it might be linear regression, transform, or anything like that. And that will depend on what your task is and how complicated your data is, and so on. And then the second thing is how you train it. So it might be supervised learning, which is where you have data that you've labeled, so it might be like in terms of the forecasting, the price, so the sales. It might be you've got previous data on the sales, so the outcome is the sales. You've already got labels on. You have labels on the inputs like the weather, and you train it on that. And the supervised learning, you make it a prediction and you tell it how wrong it was, and it learns from that. Unsupervised learning might be where it's without having those labels on the data, it's clustering data. So it might be, for example, different customer segments or something. It knows that people can be clustered into this age and gender group or something like that, and it finds them itself. And then there's reinforcement learning, which is like, it's basically supervised learning, but instead of telling it what the answer was, you just either tell it no, bad algorithm, and give it a slap, or you give it a reward and say, well done. So I think for me, there's all these developments, but most of the developments are in these one of these two things. It's like slight tweaks to how you represent it, essentially. But I find that you can actually get quite far with some of the more advanced statistical models. So actually, the backbone to what we do is our Bayesian models, but they can do everything as complex as what a neural network can do, but in a much more kind of rigorous way, I would say.
Right. Okay. So let's take it back to basics. So that was a really good overview of everything machine learning. So let's pretend I'm the customer, and like you said before, I want to predict sales. Right. There's so much value in being able to sort of not only see what you sold last week, but wanting to see what you're going to sell next week based on some inputs. So what would those inputs look like? What kind of data would I need to capture? So say my problem statement is I'm a sales director and I want to predict sales for next week so that I can allocate stock, I can, organize staff, I can, anticipate forecasts and things like that. I can report back to the board, all these benefits of it. What do I do then with that problem statement? Where do I start? What do I need to start looking at? Which models do I, all that kind of thing. Where do I go from there?
Yeah, I mean, if you're that person, then I would say you have to talk to someone who knows what they're doing first. So, if it's so, in terms of what data, they should talk to someone like you. And so I think really that's the first part of it. Is like you say, the main thing that people need to do is really make sure that they define the question well. That's like 90% of it, right? Define your question really, really well. What is it you're trying to do? And if it is just something like, I want to predict next week's sales of this item, then that's pretty clear. And now you need to have an idea of what might predict it. And now it depends on what data they have, what they've been recording, right? So essentially, if it's just about forecasting, quite often the more different types of data and the more data you have, the better it will be at the forecasting. Certainly with like non-causal standard models, they need to see as many scenarios as possible, right? Because I'm trying to stay away from causal models here for now, but it's standard non-causal models are not very good at unforeseen situations. They're very good at predicting the future if the future looks a bit like the past, basically.
Right.
But they're not good otherwise. But we'll come on more to that. So really, yeah, you need quite a lot of data in terms of this is rows of data. So in that case, it would be say that weather is one of the inputs, because we know that weather is going to be something that affects people. What do you think is the effect of the weather? And it needs to learn that from previous data. And then what is next week's weather going to be? Because now the model can tell you based on that how much you're going to sell. Because if the weather's bad, people aren't going to come to your shop as much, maybe, right? So I think it's about looking at what data they have, and then thinking about, well, which variables can basically contribute or correlate. They only have to correlate. They don't have to cause if it's this problem that we're talking about, the outcome, essentially.
And the machine learning bit is me not having, as a sales director or a technical lead or whatever, to define the relationship between the input and the output, right? So I don't have to tell the model if weather is 10 degrees, then this has an effect on sales, as in sales will half. But if it's 20 degrees, then sales will double. I don't have to define those rules, right? For machine learning, it defines the rules for itself. Is that right?
That's right. The whole learning bit in the machine learning is that it's essentially learning the rules or the mapping from one thing to another. So that's that kind of middle bit I was talking earlier, where I guess I called it a functional form, kind of geeky thing to call it, but it's the way it learns the way to map those inputs onto the output, basically. So that's the model's job. And the only job that you have kind of as the business is to say, okay, talk to someone who knows what they're doing with these models and say, like, here's the question we have. Here are the data that we could probably use, and then they can tell you whether that's enough, and they can come up with the mapping, basically, and these models and train it. And so I would say that's the main thing.
And from a user's point of view, if it was just weather versus sales, right? Sales being the output, the thing you want to predict, and weather is the input, the thing that has an effect on sales. That might be easy to define the rules, right? It would, you could do it in theory, go through and say, if it's this temperature, then it's this sales, and then extrapolate it forward. But then if you're talking dozens of inputs, so say weather, preferences, availability, all these other things that businesses obviously measure and have to rely on, then it becomes even more complicated. And that's why machine learning offers even more benefit, right? Because there's almost an infinite number of combinations between the variables that could lead to the output.
Yeah, that's right. So if you can, even if you imagine it as like a decision tree, right? So it's like, okay, you have all these potential outputs. So there are categories of how much sale, like low, medium, high, and you're trying to know from the data how do we reach which one we think it's going to be. If you have the more data that you have going in, that probably the better the prediction is going to be, but the more complicated it's going to be. You're going to have so many different kind of paths, kind of diversion there, that you're not going to be able to do it without the machine learning it for you. You're not going to be able to look at it and be able to decide that, and you certainly wouldn't be as accurate.
Okay. And so that's more regression, isn't it? Or what some people might refer to as forecasting. What about classification and sort of other machine learning problems that it can solve? Do you want to just touch on that in terms of
Yeah.
how does that work? How is it different to a regression model or a forecasting model?
Yeah, so how it's different is it's a special case of forecasting. So it's not actually different. I would say it's just a special case of it where, so actually the example I gave was basically a classification example, right? So it's exactly the same. You're forecasting, but instead you're forecasting a category instead of what we call like a continuous outcome. So instead of a variable that's a number, and it could be like anything, 1.2, 1.8, it just classifies it as either it could be like this email is spam or not spam, or it could be this, high, low, medium, that kind of thing. So classification is just where you send in the data, and the result it gives you is a classification of something like that, spam or not spam, and that's it really. So there's not a lot of difference between it. There's a difference in how you model it, in that you would use something like the way that you process the data at the end of a neural network or a regression model would be different. But essentially, it's just a special case where you have categorical outcome.
So essentially, going back to our sales forecasting, if I wanted to predict sales volume in pounds, it would be a regression model, like a forecasting model, right? So it would be £32,083 and 72 pence, a
Yeah.
number. But a classification would either be good sales day versus bad sales day, or something like that. Okay, so that's interesting. So what are the weaknesses of these? Are there any, or is it as good as it seems, of these sort of standard traditional regression and classification models that are available?
Yeah, so I guess I guess for me, like regression is more like a statistical model, whereas something like it would be the same if you had like a neural network and you were inputting the data, and you were getting like the pounds predicted. In that case, you might use something like back propagation or something else, but it is all essentially the same as like a regression. So I call those forecasting models, and those are prediction models, and they're based on correlations in the data. So this is where we can get onto the causal machine learning, which is that what you can do with those models is what we've been talking about. They're fine if you're focused only on the outcome, and you want to predict the outcome. What they're not fine for is if you want to explain why the outcome came about, or if you want to shape the outcome. You want to actually make actions in the real world that change the outcome. So, for example, you say, "Oh, okay, we've predicted that next week the sales are going to go down. What can we do to make the sales go up?" You can't do that with non-causal, with standard AI, because because in the real world, when you make a change, there are knock-on cause and effects all the way up to the outcome. And these models, the standard models, basically don't consider this. They will come. They essentially put all of the data through what you can think of it as a blender, and they don't care how they mix up all the data together. They mix it up any way they can to best predict the outcome. And all a model knows about and all it cares about is getting close to the right answer on the outcome. And it doesn't have to do that in a way that represents the way that actually those things affect it in the real world, right? So, so in a way, it comes up with its own world model, that doesn't represent the way that things actually work in the real world. And then the difference with causal models is that causal models try to do that in a way that does actually map on to the real world, so that you can shape the outcomes, right? So with causal machine learning, you can shape the outcomes, you can understand how they came about rather than only forecast them. So causal models can also forecast, but they can also shape. They can tell you like what exact actions to take. They can tell you the optimal actions to take in a scenario. They can tell you what if scenarios. They can even look back and say, you did this thing, what would have happened if you'd done something different, right? So in a way, causal AI has a holistic understanding of the system, whereas what standard AI does basically is treat all of the inputs, so these are the things you're using to predict the outcome, as being completely independent of each other. So it actually, standard machine learning and AI assumes that all of the inputs have the potential to cause the output, but not each other, right? And that's a big problem, because understanding cause and effect is essential for data-driven decision making or optimization of a system, or actually even just for forecasting in a changing environment, or safety critical environment. Again, it's better for that. And I think maybe this is a point where I can kind of share my screen and take you through kind of a bit of an example of this. So if we have a look at this, okay, can you see this okay?
I can, yeah.
Okay, so I'm just going to show you some really, really simple examples, right? It's not as simple as this fully, but like this will just give you the general idea. Imagine that you have a system where you have like one variable here, and in the real world, it causes this variable here, right? So a change to this will cause some change in this, and some change in this will cause some change to your output. This is the thing you're trying to predict, but also know how to change, right? Now, this might be some examples we've been working with is like production lines, right? You've got a production line, you've got some raw ingredients that go into it. This might be the first machine on the production line, does some things as a blower or something like that, and goes into the next one. And then finally you get your yield or something like that. Now, what would happen is if you wanted to, this is your outcome that you're training it on. Now, if you put both A and B, both of these machines or the settings on these machines into a standard non-causal model, and it can be any non-causal model, right? It doesn't matter what the representation is. What it will tell you is that A has no effect on the output whatsoever, right? It will say that B does, but it will completely miss that A does. And it might be that A is the only thing you can actually make any changes to or tune into. And the reason is this is what's called a mediator, right? A mediator is something that essentially it mediates a cause from here to here to here. It passes on information. In this case, the production line, right? Something you change something here, and it will have an impact on what happens here. Standard machine learning, it completely ignores that. But causal AI would know that if you change this, it changes the output, because you can actually understand how these things relate. Okay, so that's one example.
So just on that then, Dan, so something like if I was running a electronics store, right, and I had a sale on, say that's input A, and I reduced every item by 20%.
Yeah.
That would then influence perhaps more people coming into the store, which would then influence sales. Is that am I getting on the right lines there?
Yeah, it could be something like that, or it could be like say that A was how long someone's used the system for, right? So it might be you've got a software platform and they've used the system. This is like used a long time and not very much time, and the output might be customer churn, right? So in that case, there might be some direct arrow here, because if they used it for a long time, they might be more likely to use it in the future. But also B here might be something like bugs experienced or something like that. So the longer you use the system, the more likely you are to experience a bug. The more likely you are to experience a bug, maybe the more likely you are to leave. If you include B here in the model, it cuts off this entire causal route here. So all you will get is the direct effect of it on it here. But really, there's a lot going on here. So you'll actually, this can have the effect of completely flipping the result and all sorts like that.
Okay. So time used and bugs experienced are both inputs that can be used to predict maybe churn or whatever on the platform. But
Yeah,
also time used also influences number of bugs experienced. So there's a relationship between those two variables too.
that's right. So if you put this into like a normal machine learning model, what it would look like essentially is this. Right?
Right.
It doesn't know that the longer you it can't know basically that the longer you use the system, the more likely you are to experience bugs. These two things can interact together to give this, but they can't. One can't cause the other, right?
Okay.
And that's a big problem. What it means is that if you use standard machine learning on this, it'll be fine for predicting the output, but it's not fine if you say, okay, what's the impact of A on the output, right? Because you have to know what its impact is on B because
Right.
it's due to the output, and only causal AI can do that.
And
So that's
the,
one thing.
and again, just sorry, quickly on that before we move on, but that it might not just be A and B, it might be A through to Z and
Yeah,
Z26, right? It might be
that's right.
multiple inputs, not just two, right?
Yeah,
Obviously,
yeah, that's right. I
yeah.
mean, you might also have some more down here that are basically, like this as well. If you actually include any of these in the model, it blocks the entire causal chain down here. So again, the effect of this on this, you won't actually know. You'll be fine for predicting this, but you won't be fine for knowing what change do I need to make, what action can I take in the real world to actually have some effect on this output, rather than just predicting it.
And just quickly on that, Dan, as well, for anyone a little bit more technical watching, this is starting to look a little bit more like a neural network diagram. Is there any relationships there? Is it closer to neural networks or neural networks closer to this, or is it just completely different? It's just the images look the same.
It's completely different. The only similarity is that we're representing it with arrows and circles. So I'll show you the difference basically. So because it's a good question. So really, what you have, imagine we have something like this. Put another node on here. So imagine you would just have these two variables, right? Now, oops. So yeah, imagine now that we're using a neural network. I mean, it's a non-causal model, right?
Okay.
Now, what it would do is in here, there's a function, I'll just call F, that is a neural network, and it's learned, and this neural network in here is basically a bunch, or you might consider it to be here, right? Is the functional form for mapping whatever the values are of these variables onto this, right? So this is basically learning the shape, like how you go from those inputs to the output. And so the neural network is basically just the functional form. So it doesn't matter what, that could be a neural network, it could be a spline, Gaussian process, it could be anything like that, linear even. But the way that's different to this is that this is the causal structure, right? This is, if I make a change to this variable, how does it change the value of this variable? Now that doesn't happen. So here, for example, if you put in this causal model, if you had a neural network, you would have a neural network learning the relationship between every pair of variables instead of
Right.
just all of them to the output. So the neural network is learning the shape of the function that maps a variable onto another. This is mapping which variables can change the others. Because even in this, even if you had a neural network like in here that combines these two variables together, it only knows how to do them based on correlations. What it doesn't allow still is that this to cause this, right? Because these are causal links. They're not nothing to do with like learning functions, right? So on each of these you have a function that's been learned essentially, so that when I change this, it will now propagate through all these causal links, and each one of them would have a functional form, which might be the neural network. So that's the main difference.
So correlative, then in summary, the neural network is just trying to find the correlation and trying to combine inputs to find a correlation to the overall output that it's trying to estimate or forecast. Whereas the causal version is also looking at how the inputs cause each other to change as well. Which
Yeah,
whereas correlation models are just looking at the inputs versus the output. Causation is also looking at input versus input versus input
yeah,
versus output.
that's right. So for example, here in terms of the actual causal structure of this model, even with a neural network, the actual causal structure still would just look like this, right? So that's the
Right.
difference. Like you'd have a neural network in here that's learning how to combine these together, but none of these are causing the other one,
Yeah.
right? And that's a big difference.
When
And
when you think about it in real terms, in terms of if we actually added labels to this, it's a bit ridiculous, right? If you're trying to predict ice cream sales, to assume that there's no relationship between the weather and people by the beach would be ludicrous, right? But that's essentially what the correlation model's doing.
that's right. So that's the next example. Actually, that leads me on quite well. So this is an example of what we'd call a mediator, where you're blocking a causal effect, right? You're blocking, if I change something on this, how it changes the output. But there's other things that happen too. So that will completely mislead a non-causal model if you're using it for decision making, right? So you shouldn't use non-causal models for decision making is a key, including ChatGPT.
Especially ChatGPT.
Especially ChatGPT, yeah. I could go on about for an hour about that. But yeah, so the example you gave is of a different structure, which is equally as important, which is a confounder. So a confounder is something like this. So imagine. Oh, actually, here they should. I'm going to remove this. That should not exist. Okay, so a confounder would be something like this. If you correlate ice cream sales and shark attacks, right? So if you only put ice cream sales and shark attacks into a model, where say shark attacks is the outcome and ice cream sales is the input, it will tell you that as ice cream sales go up, shark attacks go up, right? But it's not that ice cream is making you tastier to sharks. What actually is happening is they're confounded. So a confounder is something that is ultimately a cause of each variable, right? So it's a common cause. And in this case, like you said, like weather is a common cause. When it's sunny, more ice cream sold, and when it's sunny, more people are in the water. If you don't account for this in your model, you'll think, you might think, and in a less silly scenario, you might think that something is going on, right? That you can make a change to in your business, an action that you can change the outcome with. That isn't true, right? So here it creates a correlation between the two where it doesn't exist. But imagine that there is a cause and effect even between the two. If you don't account for this common cause, it might even flip it. So this is called Simpson's paradox, right? So it actually flips the effect. One well known as actually, I'll give an example with LinkedIn actually. So on LinkedIn, there's like these premium accounts, and on these premium accounts, it says something like, people who get the premium account get like 120% more interaction with their posts or something like that. But when you look at the premium account, there's no mechanism in which it could possibly do that, right? So what's going on? Well, what's going on is it's confounded. So it's just that the type of person who would buy a premium account is also the type of person who is more interested in doing good content, right? It's a confounder, right? So it's a confounded. That relationship is meaningless, and there's no benefit to and it can't be because there's no mechanism for that, right? So this kind of thing goes on all the time, and it can be more complicated than this too. But this is a very simple example.
When marketers do statistics, Dan?
Well, and marketing is a really big one for this, right?
For your LinkedIn example.
Yeah. Well, I mean, that's right. So in marketing, it can be in their favor not to get it right.
Yeah.
Like as in that situation, yeah.
So on this then, so if I worked at Bondi Beach and I was, I don't know, the government or the tourist board, and I said, right, I want no shark attacks. That is my problem statement. I am the local government. I want to make sure there's as few shark attacks as possible so that we can ensure public safety and everyone has a nice time and people keep coming to Bondi Beach, whatever. If I was to do that with a correlation model, the standard AI that currently exists in the market with machine learning, what might I accidentally conclude as a takeaway and then take into an action step and it leads the wrong way? How could I make a mistake using correlation models?
Yeah. So for example, if in this situation you don't have a causal model that takes care of weather basically and understands that it's a confounder like this, so you'd need data on the weather basically. If you only had data on ice cream sales and shark attacks, and either you just had a dashboard and you plotted one against the other, or you correlated them to each other using a regression model, or you had a neural network that somehow learned the relationship between them. Any of these kinds of things, or you fed it into ChatGPT and said, tell me if these two things are related. It's going to say basically, and you took action on it. yeah, you might say, okay, let's close down all the ice cream stores, or put a tax on ice cream or something like that. The shark tax on ice cream. Obviously, it's a silly example, but there are
No, of
real
course.
business scenarios where this has a real effect, right? So
Yeah.
it will lead you. It could lead you to actually, if it's Simpson's paradox, is actually where the effect is flipped, right? So where there is a positive cause and effect, say, but because you haven't accounted for this confounder, it flipped and it says there's a negative one. So it can actually, in many situations, lead you to do the opposite of what's true. There's an example of this, like health and fitness apps are great examples, right? So if you do a dashboard and you just plot how much someone exercises against their cholesterol level, you find this really nice linear kind of positive correlation. So what it's basically would tell you is that the more you exercise, the higher your cholesterol level, right? And that seems completely wrong because it is, but that's what you'd get if you just did that. And the reason is it's confounded. There's a common cause of those two things, which is age. And so when you actually causally consider age, and in this you could just filter by some age groups, for example, what happens is that the effect flips. And now you can see that within each age group, the more you exercise, the lower your cholesterol. It's just that it's a common cause. So the older you get, the more you exercise, the older you get, the more you have cholesterol, higher cholesterol, basically.
Yeah.
These are scenarios where you can go wrong with this.
On that then, Dan, how do I know what I should be gathering data on versus what I shouldn't be gathering data on, right? So if we go back to the Shark Attacks ice cream sales, if I'm the tourist board, there's a lot of things I could
Mm.
capture, carbon in the sand, or how many pebbles are on the beach, or how many umbrellas there are. There's lots of things I could capture, and it would cost a fortune.
Yeah.
How do I go about finding out what's important to capture versus what's almost irrelevant?
Yeah, so so there's a few things I can say on this. One is just a lot of the time we can look at what data people already have and then draw these diagrams and then say, okay, how far can we get with it? And even if you don't have all of the variables you need, it will always, in terms of decision making, do better than non-causal AI, right? Because you've got what we would call it partial identification, but basically, at least it's less wrong, and you can probably use it to make some good decisions. Where you have missing data, you can also do things like we can systematically vary it, or we can use human domain knowledge as well on these things. And so and that also will help you make decisions. You can kind of, with these systems, integrate human knowledge with data. And I think this human interaction with data, quantitative and qualitative knowledge together, so data and people's expertise and experience and common sense, is what you can do a lot. If you wanted to actually plan something to collect data, like this is what we would do in science now, what I would do in ecology is you draw out the causal diagram first. What you do is you start with the thing or the multiple things that you're interested in that you can actually change to make an impact on, right? So you might have more than one of these. In this case, we've got one. And then you put what the outcome is that you want to change. And now what you do is you draw in any variables that you think are in between these two things, right? Like this. And again, that might be based on domain knowledge. It might be based on most of the time, just common sense will get you quite far. There are also algorithms that will learn this if you have the data already. And in anything between these two things, it doesn't have to be on a causal path. It can also be like this on a non-causal. And you think about it with knowledge of the system. So here you wouldn't include, deck chairs, because it's not going to. Ice cream sales, for example, might be a cause of deck chairs, but they're not going to be a cause of shark attacks, right? So so that's how you would do it, and you can use that to plan out the data. But as I say, a lot of the time you can do this after the fact, especially in industry. And then you can bring in data like weather data. You can always go and find historical weather data in the region from other data that you haven't collected. If it's a supply chain, which is a big application area of causal AI, they often have information you can get it on what links to what in the supply chain. If it was a production line, which machine goes to what, and so on. If it's medicine, you would bring in an expert in the area and you would talk them through this. So that's basically the only way to know what data to collect is to do that.
And is that how we can start baking in domain knowledge? Because we work with a lot of companies that have been going decades, right? And
Yeah.
nobody knows, I don't know, ice cream manufacturing or wood, carpentry, whatever it is they make or do, whatever service they provide, they know it inside out, right?
Yeah.
They know it better than we ever would because we haven't got that experience. Is this a better way then of baking that experience into the model so that it learns from what you've learned instead of using standard machine learning where you can't really give it that knowledge or that context that you know?
Exactly. So actually, with what we do, we use Bayesian models and we use the causal models. And there's actually two ways there in which you can use human expertise. And in fact, with our models, this happened with our first customer. Actually, is that we had a model that was intelligent before it even seen the data. So it would already do really well before it had seen the data, because we baked expert knowledge into it in terms of the causal structure, but also the relationship between the variables we already knew, because this was about optimizing the use of cloud compute to reduce like CO2 emissions.
Okay.
And so we already know, like, well, Jordan, basically, my co-founder, already knows a lot about cloud compute because our platform is cloud-based. And so he already had a lot of domain knowledge, and working with a customer, they have lots of domain knowledge on this. And in this collaboration, it can be sensible because already, you can already have an idea of what the possible distributions of relationships between variables are, as well as there being information in the relationships between variables. And so it really is, for me, the only approach that genuinely brings in domain experts and listens to them. It doesn't only trust the data, right? It says, yeah, we can learn from the data, but you cannot learn cause and effect from observational data alone. You need to bring in either common sense, learn the causal structure with algorithms, or bring in domain knowledge, which is and those using these kind of diagrams, it's really easy for us to do that, work with customers and bring that domain knowledge in.
That sounds great. I can see survival below. I'm very curious. Have we got another example of something different, or
Yeah,
is this the same example but different context?
it's a different example. So if you notice here, so this one had this was a common cause of two things, right? So this thing is a cause of this thing and this thing. This is the opposite way around, right? So in this case, this is notoriously hard to explain, right? This is not an intuitive concept. I'm going to explain it in a way that seems to people understand it more. So essentially, this is what's called a collider, and it's when, say that this is the variable we're interested in, this is the outcome we're interested in. Now, a collider is a thing that is caused by those two things, right? Essentially, there's more complicated structures than that too, but think of it as that, right? Now, this thing here is that's caused by these two things is a selection effect. It will select either by having it as a variable in your model, right? If you have a regression model, a neural network, if you include this variable in your model, you create a selection effect between these two variables, right? I'm going to give you an example of this right here. So, have you ever noticed that with restaurants, some of them have good food and a good location, but in general, the ones that are in a really bad location but survived tend to have really good food. You hear people saying, "Oh, I know this restaurant has great food, but you have to go, out of the way to get there," and things like that. Whereas one that's on some beautiful lake or something, it's like, yeah, okay for me.
Yeah.
So this is because of colliders, right? Our selection effects. So essentially, what you're looking at there normally is only restaurants that have survived long enough for you to be able to go to them, right? And so for those to survive, there are two causes of those restaurants surviving. There might be more, but let's look at just two. In this case, a good location or good food. And imagine you're in a bad location. Well, then to survive, you've probably got to have good food. But if you have good food, you probably don't need to be in such a good location. And also, if you're in a good location, you probably don't need to have good quality food. It's going to be enough to survive, right? So what happens is, if you look at every single restaurant there ever has been, there's no correlation and no cause and effect for sure between these two variables, location and food quality. However, if you only look at those who survived, right, then over, say, the past 2 years, it will say that there's a correlation between them, but it's not a cause and effect. It's due to including this. So if you have a model of all the restaurants there ever were, but you included like some variable that was maybe survive past 2 years, you will create a correlation between these two that doesn't exist. right? And this
Right.
this is a silly example, but again, this happens all the time. If you see a structure like this from we would call it the exposure, but like any of the things you want to take action on in the real world and the outcome where they're both causing it, this is something you should not include in the model ever. And it's just something you can include it in a causal model because it knows a causal structure, but if you include it in a non-causal model, it creates the effect I was talking about. And that's another danger of using those models. So it's a danger of what people often do with these forecasting models and non-causal models is they try to use them for decision making, and they think that the more you throw into the model, the more variables, the better. It's absolutely not the case. What you need is to know the context of the variable, essentially, because they're not causal models, and if you don't know the context, you don't know if you should throw it in or not. Causal models, it's different. As long as you're outlining the way they interact, you throw all the variables into the model. So yeah, there are ways that you can do this as well without it being a model, the way that you collect the data. So if you only collected data on those who survived more than 2 years, you would have the same effect. If you subsetted the data for it, you'd have the same effect too. But you can only know this by drawing the causal models again. So I think I'll finish there on the
No, that was interesting. It just reminds me of when everyone talks about like black box AI, right? There's in terms of they have no idea how it made the decision, but they're making some serious decisions off the back of whatever decision the AI makes, right? It has real world impact. Like I said before, you might shut down all the ice creams on Bondi Beach, ice cream sales on Bondi Beach because you think there's a relationship. Or when it comes to restaurants, again, making poor decisions based on that AI. So do you want to just touch on that for a minute in terms of how easy it is to get the wrong outcome and the wrong reasoning because you're missing that context and not using the causal model?
Yeah, so actually, yeah, you hit on two really important things there, and I'm going to kind of categorize them first into explainability of models, like understanding what they're doing,
Mhm.
and second, I'm going to talk about deployment of models. So what happens when you go past like looking at how they do on some data you've put aside and actually deploying them in the real world, and either taking their recommendations or getting them to automatically do something for you. So on the first one, on explainability, excuse me, then there is something called explainable AI, right? And this is AI where you use any model, and again, any non-causal model, and you use something, it's normally called like SHAP, but it's essentially what it does is it tries to explain what your model is doing. So for example, it will say, okay, in predicting the sales next week, what was it using the most? Oh, yeah, what features that you've input of the data was it using the most? And it might be, oh, it's used the weather quite a lot. It used last week's sales quite a lot. And it'll tell you things like that. The problem with it is it tells you what your model's doing, but it doesn't tell you what's happening in the real world, because again, it's a non-causal model, and your model's just blending the data up. And for example, if you included a confounder, so if you didn't include a confound, it's going to look very different from if you do. It doesn't really tell you what's going on. With causal models, not only can you do that and say what features are more important, it can tell you if I make a change to this feature, how much will it affect the outcome compared to something else? But not only that, it will tell you the reasoning process it took, right? Through that causal graph, you can see how thick the arrows are. For example, it will tell you it took this route. It's mainly that A affected B, which affected C, rather than A affecting it directly. So it will tell you exactly how it did it. I've even heard some people say that like large language models are explainable, but people have different idea of what they mean by it. So with that, I see a lot of people like they ask it to make a decision, it does, and they say explain the decision, and then it explains the decision in a way that seems really reasonable, but isn't the reasoning it used to come to that decision, if you know what I mean.
Yeah.
So that's another problem with that. So yeah, causal models are really much more explainable in a way that you can map onto the world, right?
Mm.
Which is what's necessary for you as a person to understand them, really. And then the second thing is about deployment, and so this is about like where it can go wrong. And I'm going to show you a really quick example of this again. So you'll know about this example. So in this example, yeah, so normally what you do, right, when you have standard AI is you have some training data. In this case, this is a training data on. We want to know from we want it to, it's a decision making problem. We want to know from the machine learning, what shall we set our heating system to, our heating and ventilation system? What settings should we do to keep the indoor temperature to some value, right, given the outdoor temperature? Something really simple in this situation. We have some indoor and outdoor temperature. We simulated this so that we can simulate what happens when you deploy in the real world. Now, normally what happens is when this is using XGBoost, but it doesn't matter what you use, neural network, anything that's non-causal will do the same as this.
From what I've seen, though, actually, Boost is a pretty good model to use from most things from what I've seen in the academic research.
Yeah, so if you look at Kaggle or anything like that, it always seems to win the forecasting problems
Yeah.
that they have. So it's really good if you have a forecasting problem. I would say it's like the go-to. So that's why I chose it, actually. Yeah, it's like the go-to for forecasting. And so yeah, what happens is the way that people typically evaluate it, they should probably use cross-validation, but what often happens is they take a chunk of the data that it's before you train it, and put it aside, so it's not trained on the data. This is their test data, and then normally what they do is they look at what on that data, on the test data that hasn't been trained on, what's the predicted heating value in this case, it's the outcome, compared to what the actual value was in the data. So then they use this to validate the model, right? And it is good for validating to see how well it predicts on historical data. So here you can see, because it's along the data points are along this diagonal, it means that the actual predicted value is quite close to the actual value it wanted to get. So that's good. However, this is not a forecasting problem. This is a decision-making problem. That's a problem now, because although this is normally the point where someone using standard machine learning would say, oh, look, it's doing really well, let's deploy it, right? The problem is, decision-making problems are not just prediction problems. They're predictions upon a change in the world, a prediction upon intervention problem, we would call it. And the problem with standard AI or standard machine learning is, as I said before, it can only predict the future if it looks like the past. If something massively changes about the system that's now outside of its training data, often doesn't do well. And here you're making it a change to the world. You're actually changing the heating based on its recommendation. So we can actually say to it, okay, we'll give you a new year of data. We want you to set the target temperature to 18 degrees. And here's what it does, right? So this is our desired temperature. And it does really badly. It's too hot and it's all over the place.
Yeah.
And I won't go into details about the causal model, but if you actually do a causal model using our platform, then here's what it does. And it's because so this is simulating deployment here, right? It's like if you actually make a change in the world, what knock-on effects does it have? And the reason it's done really badly is because it can only deal with historical data. It doesn't know what to do once you've made that change in the world it recommends, because the world looks different now. Whereas causal models, because they're not based on these fragile correlations, it can deal with situations that have not been seen before, which is why it's actually better for prediction scenarios where things can change, or you haven't seen every foreseeable situation, essentially.
Which again is super obvious when you think about it, isn't it, Dan? That you need models to be resilient because the world is ever changing. Things differ day to day. What happened last year is going to be completely different to what happened this year. I'm looking out the window now at the torrential rain, thinking, yeah, this is probably not the July we were having last year, right? So you need a model to reflect and be able to adapt and be resilient to changes that we often see in the world.
Yeah, that's right. And so these are the kind of two really key use cases for causal machine learning. Even if it's just a pure forecasting problem, we want it to be robust against big changes. And if it's a decision-making problem, where you're going to be making a change, because that's the whole purpose of it. So the system is going to change that it's trying to model, and now it hasn't seen that scenario before, so it needs to deal with it.
I just want to address as well, Dan, accessibility to these models, because I think there's a lot of business decision makers, directors looking at getting into AI, thinking we need to spend X amount on some new SaaS system and everything. AI only exists within CRMs and ERPs, and that's the only way they can get access to it, right? Where somebody else has made a model for them and they're buying into it, but it's not really adapted to their circumstances or situation. How hard is it to get started? Is there a lot of barriers to entry for businesses that want to go, yeah, Dan, this sounds great. This is exactly what we want. But, where do we start? How do we get started? What access can we get to these models?
Yeah, so traditional. I mean, this is a reason we started Causa actually. So traditionally, there are two things. First, it's a bit more of a scientific way of doing AI instead of brute force, and so it's tended not to be in the wheelhouse of your standard data scientist, even AI researcher. And so most people see everything as a forecasting problem. So I see a lot of misuse of correlative models or non-causal models for decision making because of that. And so I think one of the problems is if you go to a company that doesn't know about this, they will recommend their forecasting model for a decision making problem, and it will give you wrong results. But normally what happens is it's decorated with some storytelling and you don't know it, and that's a problem until much later. And the other thing is that they haven't been made very accessible as well, because it's fairly new in a way to the machine learning world in terms of it hasn't got full adoption. So the diagrams that I showed you before were drawn in our UX. So it's a no code model builder. So we work with companies to do this. So we'll work with them to help draw out these models. And as you can see, we bring in their domain knowledge and talk with them about it. It's not just about brute force trusting the data. We trust them as well and their knowledge as well as their data. And so we can just work with them with these simple diagrams, and that's it. That diagram actually generates the model in code that they can. We can either create a quick Streamlit app for them, or what we tend to do is bake that model into their own software so that their software is powered with it, and it's through our API. So it's as easy as that. So we've worked really hard to make it that these kind of advanced causal models are accessible. We've even given a causal background to a large language model as well, because they can't use them, but you can actually query our causal models using a large language model too.
Because I think that's the main reason that ChatGPT is so popular, right? It's that accessibility. Large language models existed before ChatGPT. It's not a new technology per se, but the accessibility of just logging in and you're away, I think is really what's brought those barriers down. You don't have to go through academic research papers and learn how to code anymore. So you've worked really hard to make these easily accessible to companies via APIs and through your UX, so you can get started straight away almost.
Yeah, so for example, if someone's got a kind of a machine learning team, then they can get started really quickly. If they don't, and we're kind of aiming a lot of developers who don't know much about machine learning or AI, but know that they could use it. Well, this is where we'll work with them and help them to build these models that would then power them, and it can be quite quick using these interfaces to build these models and then and integrate with their systems.
So it's more accurate. It's just as accessible, if not more accessible. It's more transparent, ethical. I want to talk ethics briefly. I'm conscious of time, and we do have an ethics webinar episode coming up in a few weeks. But what impact does causal models have on ethics, if any?
Yeah, so I think it's interesting. Yeah, so when people are talking about ethics in AI, these are the kinds of things they tend to neglect, I think. There's a lot of with all of the exaggerated hype about Gen AI, there's also been a lot of disillusionment and fear about it too, and probably rightly so. Given some of its misuse, but there's also been like a lot of regulation because of that. And so, in terms of fairness, in fact, there's a lot of algorithms that are biased out there. So it's so horrific that people would use it for like shortlisting CVs and stuff like that, right? Because there's all these biases in it. If you use ChatGPT to shortlist CVs or a neural network, it's going to be really biased. And with causal AI, what you can do is when you do these kind of diagrams, well, you can see maybe something is a confounder, and you can remove it, right? And so to know whether something is a cause or a confound or whatever, you have to do these diagrams. So, for example, if you do explainable AI on a neural network, and you can see, okay, it's using gender to predict whether you should shortlist the CV or not. Is that a good thing or a bad thing? It could be either, right? And because it could be debiasing, or it could be using it to bias, but you don't know it until you know where it is in that causal structure, essentially, or you can at least hypothesize and see what its reasoning process is. In fact, there's a whole in academia. There's a whole kind of research area which is all about ethical AI and debiasing. And for that, they use causal AI because it is literally the only way that you can do that. And so I think it has a big role there. The other role is in the explainability. Again, explainability it's a bit meaningless to know what your algorithm's doing unless you can understand what that means for the world.
Mm.
And so I think that that's the second area where it's really useful as well. And then again, there's a human in the loop at the beginning, but further along as well. And I think that's a big part of it. If you're using it for anything like that, which ideally you wouldn't, but if you are, there's going to be some scenarios where you have to use it for something where there's a potential for bias. You really want to understand and remove the bias, and the only way you can do that is with causal AI, really.
Great. So it's more accurate, it's more accessible, it's explainable, it's ethical. Great. I'm sold as a business owner. So what's next? How do I how do I get in touch? How do I start working with these? Anything like that? What could I do?
Yeah, so you'll see on the page here. So there's a link to our webpage. It's causa.tech. So if you go there, there's loads of information. We have a few blogs you can go through with some different use cases. If you're a developer, you can have a look through the manual, see how easy it is to use. But also, I'm happy to talk to anyone about this at any point and see whether it's right for you.
Yeah, fantastic, fantastic. And if anyone's struggling with getting the data ready, because that's a large part of it, right? And a lot of businesses don't always have data teams and data scientists working around the clock. So if you're struggling and you want to start getting involved with Dan's causal AI models and things like that, get in touch with myself and we can have a chat and look at how we can start introducing data infrastructure and improving your data sets so that we can pass them off to Dan and he can create all these wonderful, ethical, accurate causal models. So fantastic. But great to have you on, Dan. Really enjoyed this last hour. I hope everyone watching has learned something. But yes, thank you for coming on.
Thanks a lot, Elliot.